In the last video, we talked about what makes an acid and a base and how you can add a positive or remove a negative to make an acid, and you can remove a positive or add a negative to create a negative. So acids and bases have a couple ways of occurring, but today I want to talk about what acid strength and base strength is. So I'm going to show you this formula I wrote out and then backed up so I could paste it in quickly. This is the classic one. You should know this from general chemistry, but just as a refresher, this hydrogen here is removed from an acid and becomes a conjugate base with a negative charge because the hydrogen disappeared and left the electron with it behind. And the hydrogen came over here and attached to water and made H3O. So you took a proton off the acid and added it to water. Now we have a positive and a negative. Then this in the center here reminds us that it goes back and forth. It's not like it just happens one time. But how strong is an acid? It's important if you get something on yourself to know right away how much you should be worried. If you put a drop of hydrofluoric acid on the palm of your hand, it'll go all the way through and out the back in under a minute. You might want to be aware of that. Hydrofluoric acid, not good for the body. So why would that be? Well, if I want to calculate the Ka, on the top we're just going to put the conjugates that we get, which is the hydronium and the acid anion that became a conjugate base, and we're going to divide it by how much of the acid's actually left. And this should actually make sense because if I want to know how strong an acid is, it should be willing to disseminate in water. So we put that number on top, and then we keep how much of the concentration we have on the bottom left, and that tells us a value. If it disseminated, then we're going to have big numbers on top and small numbers on bottom. We're going to get a big giant number. If it's a weak acid, then the original acid is going to stay mostly as an acid and might produce a little of this. You're going to get a small number. You're going to get some kind of a fraction. And that number can really, really vary. You can get anywhere from like 1.2 times 10 to the negative 16 to 2 times 10 to the 12. That is in order of like a molecule compared to a planet. And we just can't have that. So we don't use the Ka, we use a pKa. For the same reason that you don't talk about how far you drove in feet, because there's no reason about talking about driving 1 billion feet. You drove 3 miles. See what I'm saying? So the pKa is the negative log of this value. And I actually have a chart I want to show you here to give you a better idea, just kind of get an intrinsic feeling for it. And I like this chart because it shows us two things. Let's take something like ethanol, whose pKa is a bigger number. 16 is towards the top here. It shows at the same time that it's a weaker acid and that it's a stronger base, because these kind of imply the same thing with each other. If I take this away, notice something. If it's not willing to become this, then it's willing to stay this. So how would you get much of a conjugate base if you're not able to get rid of the original acid? They're the two sides of the same coin. So if I show you this ethanol, if it's going to have a high pKa, then it's not just going to be a stronger base, it's also going to be a weaker acid for the same reason. Let's draw that arrow a little bit more relevant there. And if I come down to the bottom, well, you've heard of nitric and hydrochloric acid, for instance. They're not going to be very strong bases because they're going to want to be an acid. Nitric acid at negative 1.3, which, by the way, compared to 16, they're still in the same general number range. It's not 1/trillionth of a trillionth versus 10 billion. These are similar number scale. Yeah, anything in the negative range is going to be a pretty strong, damn strong acid. Phosphoric acid's a strong acid at 2, so anything around 2 and below, you're going to have strong acids. Yeah, over here. And a strong acid is going to want to form the conjugate acid and base forms. So you're not going to see much of the original acid in there. And as a consequence, when I look at this chart, you are going to see something like, let's say, see this chloride ion here? The chloride ion is not really going to want to become hydrochloric acid. Chlorine's pretty happy with an electron on it. It's just because you put it in water, it's not just going to give it away. Chlorine loves to take ions. You're going to have to try really hard to make hydrochloric acid out of a chloride ion. It's not really going to want to go the other direction. So just as you're understanding kind of an intuitive understanding of this equation, just keep it in mind that strong acids are going to form these conjugate acid and base forms. You're going to have a lot of ions in your solution, and that's going to be a lot of fun for us to play with in the next video. To watch this full playlist in order, click on the video here on the left, or to go to the next video, just click on the video here on the right.